Good morning, and it is wonderful to welcome you to this next edition of Nano Explorations. My name is Vladimir Bulovic. I'm the director of MIT.nano and have the joy and the privilege of hosting these seminars. Today, our speaker is Dr. Chris Foy. He has recently graduated from MIT, from the group of Professor Dirk England. And today's talk he'll deliver is on solid-state spin-integrated circuits for quantum sensing and control. Chris is presently a technical staff at Lincoln Labs, and indeed carries the knowledge and the experience of MIT into the next set of adventures. We do have a full house, so Chris, do please take over.
Thanks for the introduction. My talk will be on my research-developed solid-state spin-integrated circuits for quantum sensing control, as was just mentioned. These devices are enabled by nanoscale quantum sensors called the nitrogen-vacancy center in Diamond, or NV center. Before I begin, I'd like to thank my co-authors, in particular Dongyu, Linon, Kevin, Mohammed, and Shai, who have worked with me a lot over the years and made a lot of this work possible. So when people think quantum or quantum sensing, they tend to think of huge optical setups built on optical tables shown like something like this, or cryogenic systems. And we really want to see these kind of quantum systems miniaturized so that they can one day maybe put in phones, drones, or cars. You know, just make them more applicable. And so to do that, though, a few challenges have to be met. We need systems that are transportable, autonomous, robust, as well as having high bandwidth. To meet these challenges, we want to leverage the amazing advances that have happened in integrated electronics over the last 70 years or so, with the development of very powerful, modern CPUs that have grown to impact almost every aspect of modern life. Some of the advantages of integrated electronics, and the ones that we'll be focusing on, is that these systems are very scalable, as well as coming with custom architectures, so we can really design them to meet our needs. And we want to use these advantages to create quantum control hardware to control these quantum systems. And this way, integrated electronics offers an efficient quantum sensing platform, making these kind of NV quantum sensors easier to use while expanding their functionality. Likewise, we want to use the advantages of NV quantum sensors with their long coherence time, which correlates to high sensitivity, their ability to sense multiple parameters, magnetic field and temperature, and their high spatial resolution to act as diagnostic probes of these CPUs, right? Solving some of their key issues. This is shown here with a thermal image of Intel's 7th generation CPU chip, where in the best case, poor thermal management will throttle device performance. In the worst case, this excess heat can lead to irreparable damage, as shown here. And so we want to solve these kinds of issues. In the IEEE roadmap for heterogeneous integration, they identified two challenges facing integrated electronics, which is their need for better device characterization to improve device reliability. And we feel these quantum sensors have a unique advantage to solve these issues. Thus, we identify the synergistic relationship between integrated electronics and NV centers, where ICs can act as quantum control hardware to address the challenges facing quantum sensors, and likewise, we can use the advantages of quantum sensors to address the challenges facing integrated electronics. This symbiotic relationship, where spin systems both improve and are advanced by modern microprocessing techniques, is an integral component toward realizing next-generation quantum sensing platforms based on NV spin ensembles. This new device classification we name solid-state spin-integrated circuits, or S-cubed ICs. Consequently, this talk will focus on two experiments that basically push the development of S-cubed ICs. The first, integrated NV centers, which were hosted in nanodiamonds with high-power electronics to elucidate functional device behavior at the microscopic scale. The second integrated the essential components of an NV spin microscope, spin control and detection, with complementary metal oxide semiconductors, CMOS. This quantum sensing chip prototype, which is shown here, combines the exceptional sensitivity of NV centers with the robustness and scalability of CMOS. So what is the NV? The NV is hosted within diamond, right? And it's comprised of a nitrogen atom that is nearby a vacancy within the lattice. And the NV lies along the axis here. Similar to an atom, it has an energy level diagram, which is shown. It has a spin triplet ground state, and when it's excited by green light and it's in the zero state, it will decay back down to the zero state through the emission of a red photon. However, and this is key, if it's in the plus or minus 1 state and it's excited, right, then it has a chance to couple to this metastable state, where it can relax back down to the zero state through the emission of an IR photon or a phonon. What this means is that the NV has spin-dependent fluorescence. If it's in the plus or minus 1 state, it will on average have less light than if it's in the zero state where it can just relax back down. Thus, the zero state is called the bright state, and the plus or minus 1 state is called the dark state. So how do we experimentally perform sensing with the NV center? So if the NV emits some baseline level of fluorescence, as we sweep the microwave carrier frequency, then we'll see a drop in fluorescence when the frequency is resonant with the NV's magnetic resonances. At this resonance frequency we call D, and at room temperature is approximately 2.87 gigahertz. The deeper this transition and the narrower this line width and the less noise on this measurement, the more sensitive the NV is. And this process of optically detecting the NV's magnetic resonances we call ODMR, and these curves are called ODMR curves. If we were to increase the magnetic field from some zero value to some non-zero value, it would lift the degeneracy of the NV's plus or minus 1 spin states to the Zeeman effect. In the ODMR curve, we'd see a splitting in the resonances, where the split in frequency is proportional to this non-zero magnetic field, where BZ in this case is the projection of an external magnetic field along the NV's axis. And so BZ is what we measure. If you were to increase the temperature, you would see a shifting of the ODMR curve D to lower microwave frequencies, right? Where before it was here, it now shifts to here. In contrast, this contrasts to the splitting effect caused by magnetic fields. Because these two parameters affect the ODMR curve independently, they allow for simultaneous measurements of the NV's local magnetic and thermal environment. And that's going to be very important later on as we use this for sensing and imaging. So actually, how do we convert this from a particular NV to now generate images, which is what we're interested in? If we have a fluorescence image where all these points here are NV centers, if we take fluorescence images while sweeping the microwave frequency, if we look at a particular point, we would see the following curve, where we're looking at the fluorescence at that point as we sweep the microwave field, right, shown here. By fitting these curves, we can get the magnetic field and temperature at this location. Similarly at a second location and similarly at a third. Doing this across our field of view allows us to generate images of the magnetic field and temperature by fitting the ODMR curve at every single pixel. I'm not going to go into detail of how this fit is happening, but I can talk about it after my talk if there's interest. So how do we use these systems for applications? So if you look at a particular device, in this case a field effect transistor, you have a drain, a gate, and a source. And there's some electrical current flowing, generating a magnetic field. This electrical current is going to generate Joule heating, which is going to cause some geometry-dependent thermal profile. And based on the challenges facing ICs, we want to be able to study this situation and figure out, what is causing device degradation due to this electrical current. So we do this by taking NVs, which are nanodiamonds, which are small nanoscopic bits of diamond. They are suspended in solution, and we just pipette them onto the surface of our integrated circuit. This is shown here with these little blue dots, okay? If we look at a particular field of view, we get the following fluorescence image. And we're going to convert these fluorescence images, as I just explained, into images of the magnetic field and temperature across this chip. And this allows us to study what's happening to the magnetic field and temperature here. This process we call quantum conformally attached thermomagnetic imaging, or QCAT imaging. And we're going to use QCAT imaging throughout this talk to study systems of increasingly complex thermomagnetic environments across a variety of samples. Okay, so we're going to start with looking at a relatively simple system that is actually simulatable. And so this system is just basically a micro-fabricated gold structure on top of a glass substrate with a kinked region here. This is otherwise known as a fuse. And so electrical current is going to flow, and it's going to increase in intensity here, and that's going to cause some joule heating. And this is going to cause a complex thermomagnetic environment here, which is what we want to study. And again, what's important about this structure is that it's actually simulatable. That's not going to be the case for other systems. If we look at a fluorescence image of our structure, I've identified the gold in the glass. Here's an SEM of a similar structure both before and after the nanodiamonds were deposited. You can see a very nice uniform film of nanodiamonds on the surface. Here's an image of the magnetic field of our field of view. Let me walk you through what you're seeing. So you can see there's higher magnetic field here. That's because the current density is increasing as it goes through the kink. In addition, you can see high magnetic field here on the edges. This is because if you remember your curl from your Maxwell's equations, the magnetic field lines are curling and constructively adding into the page. So you see a high magnetic field here. This is seen also in the simulations. Likewise, we can measure the temperature, and you can see the temperature is hottest here, where the electrical current density is highest as expected. And this also matches simulations. Now we're going to move on to a system where expand QCAT imaging beyond these kind of proof of principle experiments. So we're going to image a technologically important problem where the interplay between temperature and electrical current is crucial, and QCAT's wide field magnetic field and temperature imaging capabilities is essential, and that's GaN HEMTS. So GaN is an interesting material because there's a very high breakdown voltage across all operating frequencies as compared to silicon. And it's not just, something that's in the lab. There's actually commercial devices being made by GaN, right? This is an image of a device, a spin-off company, Cambridge Electronics, done from Thomas Palacios' group here at MIT. The problem is GaN has very intense thermal management problems. If you look at its mean time to failure as a function of peak temperature, there's an exponential dependence. This means that even small reductions in peak temperature can increase device lifetime by orders of magnitude. Compounding this problem is the fact that these devices are not very simulatable. Okay, so you really need to go into the lab and actually measure what the peak temperature is, right? And then you can feed back on that in terms of device fabrication or device layouting, right? And so that's what we're going to do. So here's a schematic of our experiment. So I've identified, here's a GaN channel, and I've identified the source, gate, and drain. Here's a cross-section of our structure where the AlGaN barrier, GaN channel, and two-dimensional gas is highlighted on top of the substrate. We're going to electrically ground the source while applying voltage on the gate, and then we're going to couple in power into the drain. This generates heat dissipation problems, so we're going to thermally ground the backside of the chip. This is incredibly important because these devices fail very, very fast. They get very, very hot. We're also going to couple in our 3 gigahertz driving frequency to drive the NVs. And then we're just going to deposit them onto the surface and image their red fluorescence with just standard commercial cameras. Okay, here's an SEM of a so-called multi-finger GaN HEMT sold by Cree Electronics as a commercial device. Identify the source, gate, and drain across this device. And what's happening is we're going to couple in electrical current here. It's going to flow into the drain and then fall across the GaN channel into the source. So come in and fall, right? Like this. If we look at the magnetic field image, you see the following images. And so this kind of puzzled us for a little bit, but I think we finally have the understanding as to why the magnetic field looks the way it does. So electrical current flows into the drain and then falls across into the source. The resistance across the GaN channel is orders of magnitude higher than the resistance of this metal contact. So there's very little penalty for the electrons to flow a little bit further before crossing over. So you can kind of model this as an infinite number of parallel resistors, right? So the electrical current is going to flow, cross over, and then continue on. This means that there is a linearly decreasing electrical current across the channel width, and thus a linearly decreasing magnetic field. You can see an image of we don't have to stick to such low magnification, we can zoom into higher mag. And here you can elucidate the finer structure of the magnetic field as electrical current flows and curls around this bend here. You can also see a very uniform magnetic field across the channel length as expected. Simultaneously, we can measure the temperature and get the peak temperature, which is around 90 degrees for this electrical power. Increasing the electrical power, you can see the temperature spikes to 150 degrees Celsius or so. Looking at the peak temperature of this device as a function of electrical power, we measure a thermal resistance of 73 Celsius per watt, right? Which was exactly what was been measured previously with GAN micro-Raman microscopy. Unlike micro-Raman microscopy, we get not just a point, but we also get an image. Likewise, we also get the magnetic field image, which allows us to understand better what the electrical current distribution is doing. So in summary, the properties of this technique is that it gives us a wide field of view, it works independent of the material, it has a large temperature range, it gives a sub-micron spatial resolution, it can probe the surface temperature, and can give us nanosecond temporal resolution. These qualities together combine to be very impactful for a variety of fields such as microelectronics, lithium-ion batteries, or advanced TECs. At the device level, QCAD imaging helps understand the working principle, lifetime, and failure mechanism of these kinds of devices, with a variety of applications shown here. So I talked about how we can use the advantages of these quantum sensors to work as diagnostic probes to try and meet the challenges of integrated electronics. Now I'm going to flip it around and talk about how we can use the advantages of integrated electronics to create quantum control hardware to kind of meet the challenges of quantum sensing with the co-integration of these components with these kind of quantum sensors. And so that's what I'm going to show next. So if we were to map the phase space of magnetometers, where on the y-axis we have system scale and on the x-axis we have magnetic sensitivity, we would see that there are two groupings. The first are these kind of very large systems, such as squids and atomic vapors, right, that are very bulky but very, very sensitive. Then there's a second grouping here, flux gate, GMR, and Hall effect sensors, which are not the most sensitive, but are very, very small. And it's the second group which is particularly ripe for disruption because there's no Moore's law for magnetometers. And these systems, you know, over the last 2 decades or so have really only had incremental improvements. And so we really want to get to this lower left-hand quadrant. So when we look at the current state of affairs for NV centers and Diamond, you know, on optical breadboard experiments, etc., we can see that they're neither the smallest nor the most sensitive. But because they're a solid state system, we feel they have a better roadmap to get to this bottom left-hand quadrant, right? And so that's what we're going to talk about for the rest of this talk. How do we take these solid state defect centers and bring them down to this lower left-hand quadrant and make really integrated compact systems? So the problem is that NVs require several discrete components. You know, you have your signal generators, your antennas, your detectors, your filters, you know, you have your green lasers, and these all come together to make the NV optical spin microscopes that we know and love, and that I was using previously on my previous work in this talk. But they also come together to make a mess. And this is just a rat's nest of cables, actually a real image from my setup, you know, before all this coronavirus stuff happened and before I graduated. And we just kind of want to get away from all this, right? And we want to make something like this, which is an integrated solution, which combines the majority of these discrete components, right, into a compact sensing architecture, which enables precision magnetometry. And this is kind of the direction we kind of want to go in. So the schematic of our chip is shown here. So we start with microwave signal generation. We feed this into a driver. It couples into a microwave ring structure, at the center of which we're going to have our diamond, our filters, and our readout circuitry. So a cross section of the chip is shown here. And what's important to understand is these chips are fundamentally three-dimensional. You know, we have a diamond on top with some incident green light. We have a microwave coupling structure, an optical filter to filter out the green pump. The red light transmits through and then is detected by a photodiode, which allows us to have on-chip ODMR and sensing. So here's a micrograph of our second generation chip. I'm not going to go into a lot of details of all the improvements we made over the first generation, but I will say it was a TSMC 65 nanometer CMOS process. It had an area of 1 millimeter by 1.5 millimeters. And it had a lot of improvements, like we increased the sensing area, we improved the filtering, and we did some quality of life improvements to make the experiment easier. It had a total DC power consumption of 40 milliwatts electrical and 200 milliwatts optical. So the first component of sensing is the microwave delivery mechanism. And so for sensing, you really want to coherently drive your entire NV ensemble so they're in phase. This means having a very high microwave field uniformity. Ideally, you might think of something like a current sheet, right, where you have electrical current flowing in the x direction, and then through Maxwell's equations, you have a curl such that the magnetic field all points in the negative y direction, right? This is a very uniform magnetic field. The problem, though, is this has 0% fill factor. None of the incident light can go through this metal structure and then be detected. So as a compromise, we use an infinite and uniform current sheet. And if the pitch between these metal wires is very small compared to the wavelength of the magnetic field, then to a good approximation, this is basically this, right? So that's good, but the problem is that while in principle this works, in practice, there's no such thing as an infinite array of current-carrying wires, right? You can only have a finite number of current-carrying wires unless you're going to have degradations on the edges due to these to the lack of the finite size of the array, right? And so these edge effects are going to degrade your uniformity. So to compensate for this, we created these compensating barriers. So we have two groups. Group C is what I just mentioned, this infinite array. And then we have another group, Group D, which is shown here, which has more current. So there's more current here to compensate for the fact that the array is not infinite. And so if you look at the magnetic field profile as a function of distance from the center of the array, you can see that the magnetic field is much higher here. This is Group D. So the magnetic field is higher here. Then we have this very uniform Group C region here where the magnetic field is better than 95% uniformity. We don't want light from these non-uniform areas, so we put metal walls below our grating to block out any light from being detected outside. And this gave us better than 95% uniformity with a 50% fill factor being achieved. And what's very important is this is a very scalable design, right? It can be scaled up and tiled across the surface of a chip up to the commercial 2mm by 2mm length scales of like normal diamond that we can buy, right? So we don't have to stick to these relatively small length scales. In principle, with more money, we can buy more area and make a bigger chip. So we want to filter out the green pump. There's only so many degrees of freedom we have, right? So we're constrained by the TSMC 65 nanometer process. So the degree of freedom we have is the spacing between metal wires, right? We can't change the material itself or the width of the wire, but we can change the spacing. And so what we can do is by tuning the spacing between adjacent wires, we can have it selectively couple different wavelengths of light to the plasmon modes of this metal, right? This is shown here in the FDDT simulations, where green light will couple to the plasmon modes of the metal and then be extinguished, while red light will mostly be allowed to pass. And so we measure 10 dB isolation between green and red with this architecture, which is very good. So the other thing we want to do, but this is not quite good enough, so we improve the filtering further by using a so-called Talbot filter. And so the idea is that if you have some sort of grating aperture and then you shine coherent light on this grating, it's going to self-image the aperture at certain Talbot lengths away, right? Shown here in the maximum. And what we want to do is we want to put metals at these locations to block the green light from going through. And we weren't the first people to develop this idea. This had been previously used for angle-sensitive cameras, right? But in this case, instead of using them for angle-sensitive cameras, we're using them to improve filtering. And so what we did is we had the following filter stack. The first layer is our plasmonic filter, and it doubles as the first, the aperture for the Talbot filter. Then we have on metal layer 6 a metal stack, and this is placed at the location where the green light constructively adds. And then we have another metal stack placed on metal 3 to block the constructive again. This is shown in the FTD simulations where the red light is mostly allowed to pass, but the green light you can see is blocked here. So see the green light goes through, constructively interferes at the Talbot length. That's where we place metals. And then it constructively interferes again here, we place metals again. So this allows us to block a lot of the green light. If we look at filter transmission as a function of wavelength, we can see that there's very relatively little transmission at the green and relatively high transmission across the NV spectrum, right, shown here. So that's very good. And so we simulated 30 dB between green and red in isolation, and we measure 25 dB. So that's very, very good. And so here's a schematic of our completed diagram. Let me walk you through it. So we have our on-chip generated microwave fields. We have some switches to control when they're on and off. We have our current carrying wires here. Interweaved in these current carrying wires are dummy wires to create the right pitch for the plasmonic filter grating. This also doubles as the aperture for the Talbot effect, right? Shown here with layer 2 and layer 3. That filters out the green pump. The diamond is just placed directly on the surface with a groove cut to reflect the green light parallel to the surface. And then we have an on-chip photodiode that reads out the red fluorescence with some readout circuitry for on-chip ODMR. So this is kind of what we're doing here. And this is what the chip looks like. So here's a micrograph of the surface of the chip with the sensing region identified. This is before and after the diamond was picked and placed onto the surface. Here's some oil onto the surface. This allows us to adhere the diamond to the top of the chip. Here's a schematic of the measurement setup. We are coupling in green light to this optical beam splitter. We want to break off a piece of the green light to a reference photodiode. More on that in a second. The rest is going to couple into the diamond. The on-chip photodiode is going to be, its photocurrent is going to be read out with a TIA, as well as the photocurrent from this reference photodiode. Both are going to go through similar TIAs into an A and B port of a lock-in amplifier. We have an external signal generator which supplies the reference frequency of 100 megahertz to lock the on-chip PLL2. And then we take our modulation frequency for FM modulation, more on that later on, and we feed it into the lock-in. This allows us to lock to this modulation frequency. So what are we actually doing? So if we look at the fluorescence of this diamond piece here, the NVs within this diamond piece, and we sweep the carrier frequency, you see how there's a drop in fluorescence like I mentioned previously. What we're going to do is we're going to modulate the carrier frequency at FM, in this case 3 kilohertz. And we're going to look at the variation in the optical fluorescence at this modulation frequency of 3 kilohertz, right? Doing this allows us to have two advantages. The first is it allows us to reject any unmodulated DC green laser background, right? So anything that's not at this frequency of FM is just going to be rejected. And this also allows us to do a differential measurement shown here with this reference photodiode compared to the photodiode on chip. And this allows us to reduce eliminate the intensity variation due to the laser, right? Which is an order of magnitude higher than shot noise. So here's an ODMR curve with this chip at 0 magnetic field. You can see that the zero crossing point is at 2.87 gigahertz, as expected. If you apply a magnetic field, you have 4 Zeeman splittings, which causes 8 resonances, because you have 4 spin populations within a solid-state diamond, right? By measuring the different Zeeman splittings for an external magnetic field, you can completely measure and determine what B external is. So you can completely reconstruct what B external is because it's a well-defined problem, right? Completely constrained because you have 4 measurements of the magnetic field. So by doing this, we can measure the magnetic field's vector components. So here's my colleague Mohammed, and he's moving a magnet, and we're measuring in real time the magnetic field's vector components, right? And so we're tracking it as it moves, right? This is actually something that's a little bit tricky to do with commercial vector magnetometers, but we're showing doing it here. In addition, we can measure the sensitivity of our chip. So by looking at one of these resonances, we can measure the slope, in this case 15 microvolts per megahertz, and we can measure the noise floor at the zero crossing point. So we can measure the roll-off. In this case, our noise floor was 100 nanovolts per hertz once you accounted for the equivalent noise bandwidth. With the slope and the gyromagnetic ratio of the NV center, we can measure a sensitivity of 245 nanotesla per hertz. So if we were to look at the phase space again of different magnetometers, our work is squarely here. So already kind of in the ballpark of competitive with more commercial devices. If we were to improve the filtering completely, right, and max out the photodiode size to commercial diamond sizes, we'd be here. If we were to leverage the full quantum nature of our system, which I have not talked about, it would push the sensitivity to here. And then if we were to implement more more exotic readout mechanisms like all electronic readout, it'd push the sensitivity to here. So what are some applications of this kind of chip? So one that's completely novel is what I call the magnetic spectrometer. So the idea is if you have one node on this chip, at that node you can see a cross section where you have a diamond, an inductor, some filters, and a photodiode. And this can be locked to a particular magnetic field frequency. Okay, and as you look at multiple nodes tiled across the chip, you can see we're measuring multiple magnetic field frequencies, and we can do this in parallel, right? And this can go from DC down to gigahertz. Using the custom architectures of the chip, we can on the fly change what frequency it's looking at, boosting the SNR and making it look at one particular magnetic field frequency. Right, this is very interesting, and then we can then have higher SNR if particularly this frequency was of interest. In addition, we can look at magnetic field localization and like tracking. So if you have a particular magnet, it's going to be at some distance x away, and we can determine this x value by looking at how the magnetic field decreases across the chip. So this is shown here in this example where this person is using the magnetometers in an iPhone to track where this magnet's position is, right? Okay, but because the magnetometers in an iPhone are so bad, this magnet has to be very large. And so if we were to look at the evolution, but we can potentially do better compared to this with our magnetometers. So if we were to look at the evolution of NV quantum sensing, it's really only the last 20 years or so that we've progressed from these kind of original proof of principle measurements to actual commercial devices, something that, you can actually use and just buy, right? And I think that's fantastic progress. And it really shows us a very bright future for NV quantum sensing, even if I'm not part of it anymore. And so in conclusion, I just want to wrap up and say how we've used the advantages of integrated circuits to create quantum control hardware to kind of start addressing the challenges facing NV quantum sensors, and then use the advantages of NV quantum sensors to try and act as diagnostic probes to address the challenges facing integrated electronics. And so I just want to say that while this is the conclusion of my talk, I think it's really the beginning of where this platform can go and the future integration efforts that NVs can demonstrate, really pushing and advancing the state of the art for the field and establishing a foundation for future integration efforts. Maybe inspiring innovations in both application space and the development of new quantum devices. And so with that, I end my talk.
Thank you, Chris. That was fantastic. So at this point, I would like to open the floor to any questions. You can send the questions via chat, and I'll make sure I read them out for you. Alternatively, you can raise your hand, and we'll make sure we call upon you. So the floor is open for questions. Before the questions start arriving, let me just ask you on how scalable is the present process. You have used the 65 nanometer technology, and clearly this implies that you should be able to go ahead and make millions of these if needed.
Yeah, that's right.
Is there any so going in minor resolution, would that in some way assist you or otherwise better your performance?
You cut off. I
apologize. If you went to a more refined node, a smaller definition below 65 nanometers, would that in some way improve the performance?
Yes, it would. It would improve the filtering. So that's one option, or it can improve the minimum, the pitch. So the pitch was something that we would want to improve on. So that's something we can do. Yeah, so I think in terms of your larger question on how scalable the device is, the microwave delivery was the thing we were most concerned about, and I think that's pretty scalable now. I think we've kind of more or less solved that problem. We may want to increase the volume. So the solution I showed was a two-dimensional solution. In Z, it's not so scalable because it only really works close to the chip. So maybe there's something we can do where we can improve the architecture further, maybe by having a second chip, right, that would improve the uniformity in Z as well. So we can have larger diamond pieces. Another big thing that's not currently implemented at all is the laser. So that's something we can do. But the nice thing is that the current system doesn't really require a nice laser. You know, people have used LEDs or laser diodes, so we can just have that, you know, fiber coupled into the chip or something. You know, it can be on the PCB or whatever. So that's a possibility. Another possibility is at Lincoln Lab, there's been a lot of exciting work on all electrical readout schemes, which I'm not going to really go into here, but this is an option where you can completely eliminate the laser, and that would be nice because then you're just doing everything electronically. Yeah.
Okay. A question from the chat by Bob Latham. Do you have any experience in similar detection using silicon carbide? And if you do, how does it compare?
I don't understand the question. What does he mean by detection?
Well, Bob, maybe you would like to elaborate?
You mean magnetic field sensing using silicon carbide?
I believe so, the way it's phrased.
No, I haven't done anything really with silicon carbide. I know it's another material of interest, and a lot of people are looking at it, but the NVs currently right now seem to be the most promising because they're room temperature, they have a long coherence time, and there's already been like a few decades worth of work on them to get them to the point where they're actually commercializable. So I think there's just like a lot of upfront investment on NVs. And like I said, like the very first commercial devices are being implemented with them now.
The clarification is that it's silicon carbide vacancy as opposed to nitrogen vacancy.
Yeah. Oh, the silicon carbide. Yeah.
So another question, let me see there, quickly rolling in. How do you manage or factor in the proximity effects, current crowding in a parallel conductor design, and its impact on the current density variation?
I don't understand the question. You mean current carrying on the CMOS chip?
Well, you do have multiple wires right next to each other, and I guess the question is there any current crowding that you might observe in the present designs?
No, I mean the CMOS chips have certain specs, and as long as you meet the specs, the current will flow and not damage anything. And the simulations are very well matched to what you see. There's been a lot of work done on making sure the simulations for the CMOS foundries matches exactly to what you put in. So it's very garbage in, garbage out. Like whatever you put, you will get with very high yield exactly that back. So no.
Okay. Regarding the NV centers, could you comment on the density and positions of the NV centers? They are random, right? Mm-hmm. But at the same time, they do have maybe some expected amount of density. And with the integrated magnetometer, do you plan to probe the samples by placing them in close proximity to the NVs?
Yeah, so so let me talk on the first part of that. So the NV density, I think maybe you can check my paper. I think we say it there, but I think we use 0.1 ppm. So that's 0.1 parts per million nitrogen. So that corresponds to a certain coherence time if you're in the nitrogen limit. And so we chose that based on the expected Rabi frequency that we would get based on our chip. And that corresponds to the magnetic field. So we knew the magnetic field we'd get, we knew the Rabi frequency, so we chose a density. So our coherence time would be, a few factors greater than the Rabi frequency. And that's because we ultimately wanted to see Rabi oscillations with this chip. And I know that work is still ongoing even after I graduated. So that corresponds to the density. You can obviously play off the density, but if you're in the nitrogen limit, you're playing off, but in some ways you're not fully improving because you're just limited by that dephasing mechanism. So you're not improving your sensitivity, right? The second part of the question is putting NVs close for sensing. For NVs in nanodiamonds, they're deposited directly onto the surface. So they're within 50 nanometers to 100 nanometers of the surface. So that's pretty close, but you can get much closer with NVs on AFM tips, which is maybe what he was referring to. And that's what are those commercial devices. So they have an NV on an AFM tip and they scan that over the surface. So I know there's a lot of work being done with this, commercially, like I already said, but also on the research academic front. People are putting these things down to cryo, and there's been people imaging the magnetic field and current of, superconducting devices. I didn't do any of that. I did more wide field stuff. So, imaging a whole field of view at the same time. So you lose a little spatial resolution, but you gain dynamics. which I didn't talk about at all in this talk. But if there's interest, I can show a few slides on our work on imaging electron migration.
Let's maybe leave that to people exploring your paper.
Yeah.
I'll ask just one last question, given the time. Could you elaborate on the benefits of the use of the solid-state spin integrated circuits for large object electric vehicle like lithium-ion battery autonomous vehicle monitoring?
You mean monitoring in terms of monitoring their electrical current?
Yeah, I assume so, or monitoring their positioning or motion or any kind of.
Yeah, well, let's start on the second half of that. So in terms of position, you can obviously use the magnetic field lines of the Earth for navigation. And so there's a huge effort at Lincoln and other places to do this, right? So this works for GPS-denied environments. And if you remember your Maxwell's equations, the curl of the magnetic field always has to be 0. So it's very hard, if not impossible, to completely block DC magnetic fields. So you don't need line of sight, right? So even if something's like down in a mine shaft or in a tunnel or whatever, you can still use the magnetic field lines of the Earth to navigate, right? So that's one. On the first part, which is on monitoring, yes, you can, as long as it doesn't need to be a planar surface. You just need optical access. So as long as you have optical access and the microwave field doesn't interfere with your device somehow, then you can just use the nanodiamonds that are deposited on the surface to image the magnetic field and temperature of your field of view. We thought about doing this for a while, but I just never got around to doing this research project. Yeah.
Well, Chris, it's been a fantastic talk, and I really appreciate all the depth of answers you provided us in the answers to your questions. With that, I will give one more reaction on my end. Thanking you very, very much for this talk.
Yeah, hopefully you liked it.
I think it was fantastic. Again, thank you. And I do invite all of you to join us again this coming Thursday at 11 o'clock for the next Nano Explorations. Thank you all. Bye-bye.